This demo will highlight the capabilities and benefits of real-time scoring to bring greater efficiency to healthcare claims insurance processing. The key value is to be able to assess a score predictively for each and every claim during the adjudication process. Predictive models are deployed into the process pre-pay. The claims can be scored for a variety of factors, such as likelihood for claim overpayment, prioritization of claims to meet performance guarantees to various insured groups, how well provider network optimization was achieved based on claim input, care management, likelihood of an appeal if the claim is to be denied, as well as likelihood of any gap in care extending to medical cost management, with scores to assess how well utilization management goals and policies are met based on claim input and history. The bottom line is that each and every claim can be tagged with business insight that can help various lines of business within the payer organization become more efficient, avoid improper payment, anticipate workload, and gain significant efficiencies. Now we show the potential value of pre-adjudication analysis compared with post-adjudication analysis to handle improper or overpaid claims. This is an example using only sample data that does not come from an actual customer situation. First, you see the base assumptions we've made as to claims processed per day, the auto-adjudication rate, and the average payout per claim. These can, of course, be adjusted to reflect the actual equivalence for an organization. Next, you see that when applying post-adjudication analysis, we assume an incorrect paid rate of approximately 3%, which is in line with the low end of the range of industry averages. Since there is a cost as well as a risk to collecting the claim after it's been paid, we assume a $25 cost to collect and a 50% success rate on the collection. These can be adjusted as well. Based on the assumed inputs, you'll see here that in this case the total recovered amount was $168,750. Now we take the same inputs and apply a pre-adjudication analysis. This analysis is done prior to making the payment on the claim. The same incorrectly paid rate is assumed, and here we assume that the predictive scoring can catch 80% of the improper claims, which of course can be adjusted. Based on these assumed inputs, and the fact that the cost of collection on a claim that has been stopped prior to payment is zero, with the risk of not being able to collect also zero, that there is a significant amount not paid out improperly. In this case, $540,000 with a savings of approximately $371,000 daily, leading to a savings of over $100 million per year. The key here is that even if you assume much more modest catch rate using predictive scoring and a lower percentage of improper claims to be found, the savings using in-process prepay claims detection can still be quite significant. Next, we address the question of whether claims can actually be scored prepay during the adjudication without impacting SLAs for claims processing throughput. The challenge is to enhance the organization's existing claims filtering to achieve the kind of business process and savings shown in the previous example, while scoring claims prepayment and maintaining the SLAs required for claims processing throughput, as well as ensuring that the related IT resource utilization costs are acceptable. To demonstrate this capability, IBM has created a demo with a very scalable test claims environment and deployed the overpayment scoring with an in-process predictive model. We used the IBM Health Plan Data Model as the basis for the schema of sample claims data and deployed very fast, efficient, real-time predictive scoring unique to System Z advanced analytic capabilities. The results, as you will see, are very fast scoring capability, ability to scale efficiently, and ability to maintain acceptable SLAs and IT resource utilization. This kind of function can result in a higher percentage of improper payments detected prior to the payment being made, so more dollars stay in-house, provider abrasion is avoided in the reduced number of claims needing to be recovered after payment, and of course an increased ROI for client investments in the System Z environment. Next, we'll discuss why System Z is uniquely positioned to be the best platform for clients who wish to do fast, efficient analytics. The core value is determining where the data that feeds the analysis resides. If an organization has claims data, claims books of record for example, on System Z, then the real-time analytics described can produce better and more accurate scores with most current data. In addition, data movement is avoided, which reduces complexity and provides the most secure environment for sensitive data. You'll see from this figure that the ability to leverage the System Z claims book of record as both the operational transaction data as well as the key feed for operational analytics allows an organization to integrate their OLTP with analytics as well as warehousing and reporting to create a more simplified, higher performing, and more secure flow. Now, moving to a very specific use of analysis that we highlight in this demo, we see why System Z is the most optimal choice for real-time scoring. If clients have claims data residing in DB2 ZOS, they can deploy a special unique feature called the SPSS scoring adapter into the DB2 ZOS environment. Then the SPSS models can be published straight into the DB2 ZOS environment. When an application wants to initiate a score, it simply makes a SQL call that invokes the scoring algorithms, and the scoring executes inside the DB2 ZOS using the data that is already resident in DB2. Next, you see the actual product ID for ZOS that enables this function. The adapter runs as a Unix System Services process within the DB2 ZOS WLM application environment, and the scoring engine runs as a user-defined function. The inputs to the scoring function can be, and usually are, both in-flight transaction data as well as historical data for best results from predictive scoring algorithms. Here we show the performance benefits of scoring, comparing scoring co-located with the data versus moving the data to the scoring analytics. You see that the rightmost column in solid blue attained the best performance, and this is executing the score in real time within the DB2 ZOS environment that houses the data, and with calling the scoring from an application that also resides on ZOS. That was the most optimal environment, both in terms of response time as well as throughput of transactions per second. The checkered boxes show the deterioration of performance when remote scoring is used. That is, the data is in DB2 ZOS, but the scoring executes off-platform, so the data needs to be moved to the scoring analytics. The second column shows the result when data is in DB2 ZOS and we execute the score inside DB2 ZOS. However, the calling application resides off-platform. For the demo implementation, we chose the method in column 4 because it achieved the best performance results by far. Next, we show how the model for improper payments was built, showing the SPSS modeler streams with the source, processing, and output nodes. This model was specific to fraud detection, but a model for any of the uses we discussed earlier can be built as well. First, there is a SPSS stream for data preparation to identify the key predictors based on the type of model that is to be executed, and it prepares the data for real-time execution using historical input data. Next, there is the SPSS training stream to develop a resultant model and train or calibrate it with historical data, and this produces what's called a golden nugget model with top predictors. Finally, there is the scoring stream that describes the real-time scoring flow and uses the golden nugget model from the training stream. This golden nugget model is then published to the SPSS Z Enterprise scoring adapter, placing it in a UDF within the DB2ZOS environment. The final step is to call the scoring function UDF via SQL from the business process that requires a score. The business process can also implement rules to determine what action it will take based on the score results. For example, allow the claim to continue through auto-adjudication, pen the claim, or queue the claim to appropriate skill for further investigations. Next, we show a pictorial of exactly what we deployed in the demo. This shows the setup done in preparation for executing the claims with in-process scoring. In this case, we had a DB2ZOS environment that housed both historical as well as transactional claims data, and a set of slow-changing data that we refer to as lookup tables. In addition, we had deployed the SPSS Z Enterprise scoring adapter into the DB2ZOS environment. We also deployed the SPSS modeler server and its related database in a Z-Linux image and used the SPSS client on a Windows system. From an application perspective, we enabled a sample CICS COBOL application as the test claims environment in ZOS. The first step used the SPSS client, the SPSS modeler server, and access to the claims data and lookup tables to develop the predictive model. In the second step, in this model, there were some inputs that were not direct from the input claim, but rather derived based on incoming claim inputs. The model development process generates the required SQL for these input fields. In the third step, the SQL for the data preparations are inserted into the sample COBOL application. This set of SQL will query data from historical, current transaction, as well as the slow-changing lookup data tables. In the fourth step, the model is published to DB2ZOS and deployed into the IBM SPSS modeler with scoring adapter for Z Enterprise. In the fifth step, the sample COBOL test claims application is modified to include the SQL call to invoke the scoring UDF in DB2ZOS. And finally, in the sixth step, the three aspects of the application are linked together and prepared for execution. Next, we show what occurs during the test claims application execution flow. First, input claims are received into a MQQ, and the claim IDs of these claims are extracted by the sample claims application. Next, the sample claims application, in this case referred to as FRTI and FRTS, retrieve the claim information based on ID from DB2ZOS and execute the SQL necessary to prepare input data for the model. The fields that are input to the model are shown here, and in this case, most are derived fields. Next, the UDF is invoked to perform the real-time score. In this case, this step is referred to as FRTU. You'll see that the steps to prepare the input and execute the score are interactions with DB2ZOS, where the data resides as well, and that's why the process is so efficient in a ZOS environment. The results of the score, in this case likelihood of improper payment and the confidence percentage of the score, are returned and the results are placed in buckets based on confidence level for further processing. In a real application, business rules can be deployed which can determine the next best step for claims based on their score levels. The whole claims execution process we show here also has capability to scale, and the demo is able to be adjusted for workload scaling. In this demo, we simulate the process of a health insurance claim that needs to be either paid or rejected. At the time of payment, the adjudication process analyzes the claim pattern, the patient, and the provider history to detect if there is any possibility of an improper transaction. Depending on the result of the analysis, the adjudication process authorizes the payment or can pend it for further investigation, all in real time. The first part of the demo shows a manual submission of a claim to point out the data preparation phase and the scoring phase. This model is built using complementary historical data in order to achieve a high accuracy of prediction. Let's start with the execution of the KICS transaction of the submission of a single claim. First, we log on to our KICS region, KICS ZLA1, and we enter the transaction FRDQ, which simulates the claim processing. We enter the claim ID in the input field, and we initially request the function I for inquiry. As a result of this function, all the claim details appear as shown on the screen, including payment amount. For example, the claim ID 111313BD00 has been submitted on May 24, 2012 on behalf of the patient ID 514925000000018241, who is a 59-year-old male. Some of the data needs to be complemented with historical information. By requesting the function S, you can see that the initial values from the single claim are aggregated with information coming from historical data. These values are going to be the input for our model. By entering the function U, the transaction issues the SQL call to the scoring adapter. For this particular claim, we see that this claim was flagged as potentially fraudulent with a confidence level of 66%. At this point, based on business rules, the organization can determine if the claim should proceed to be paid or if further investigation is needed. In the second part of the demo, we want to show 250 virtual users logging on to two different KICS regions and concurrently submitting claims. The workload runs for 3 minutes without calling the scoring adapter to create a baseline set of information, and then it runs for another 3 minutes, adding the call to the scoring adapter for each of the invoked transactions. At the end, both the workload results for with and without the call to the scoring adapter will be compared. The workload is started by entering /hcdemo. This initiates the script to log on the virtual users and to submit the transactions to retrieve the claims. There is a setup phase. First, SMF datasets used to accumulate the SMF data for the intervals are cleared and ready for new data. Second, the MQQ hosting the input claim is cleared and then loaded with a new set of claims to be processed. Next, the 250 virtual users start logging on to the KICS region, and we let the system run for 3 minutes to stabilize the workload. For the first 3 minutes, the workload submits the FRTS transactions, which retrieve and process the claims without any scoring calls. Performance data, like response time, throughput, and CPU utilization, are collected for the interval. In the following 3 minutes, the users submit the FRTU transactions that retrieve and process the claims and score them in DB2. At the end of the 2 intervals, response time, throughput, and CPU utilization are calculated and compared against the previous interval. This gives an indication of the approximate cost of the scoring via the UDF call. For example, you can see the CPU consumption is contained. The total CPU increased by 5.04 seconds, approximately 3.03%. You can see an insignificant fluctuation in the throughput where 89 less claims have been processed in the second interval over the total number of more than 18,000 claims, and end-to-end response time has increased only 10 milliseconds. As we discussed before, this is a demo system and the performance results are impacted by the limited resources available for the demo. However, the results show that CPU throughput and response time were fairly well maintained. The bottom line is that introducing scoring into the transaction provides significant business benefit of early detection and insight while maintaining transaction SLAs and limiting additional IT resource consumption. Furthermore, you can see a distribution of the claims in different bins based on being detected as fraudulent or not, and on the confidence level provided by the model. Based on this information, further actions can be taken by the claim processing flow. Finally, we show a sample flow that highlights how a claim score can be used. A claim score done in process, real time, during adjudication generates claim insight on each and every claim that the organization receives. The scores can be fed to a rules execution server such as an ODM environment to evaluate the resulting score level based on policy or benefit impact. The score can also be fed to business logic or rules that can evaluate whether the claim should proceed with auto adjudication or have manual intervention based on key contributing factors to the score. Given the efficiency of the scoring capability on System Z, multiple scores can be generated for a given claim to produce insight on overpayment, appeals likelihood, medical cost management issues, and other areas of key interest to the payer organization. Although we discussed a scoring use case for improper payments within the healthcare space, this same structure for in-process, in-transaction scoring with real-time capability on System Z can be used across a wide variety of industries. For example, in banking, the very efficient, fast, low resource consumption of real-time scoring can provide significant benefits to organizations in areas such as online fraud detection, transaction monitoring for anomalies, and sanction screening for wire or other types of transfers. In the area of retail, real-time scoring can be used to determine best offers matched to specific customers for a more strategic, targeted marketing effort, or to enhance the customer experience with key knowledge integrating transaction history, preferences, and account information. In the government arena, scoring in real time can be used to detect potentially fraudulent or incorrect tax refunds prior to the refund being issued, and to detect prepay issues with improper Medicare or Medicaid benefits. These are just a few examples of how real-time, in-process scoring can bring early, actionable insight to your organization. For further discussion or questions, please contact your IBM representatives.